A very good morning, good afternoon, or good evening, depending on your geographical locations. Welcome to the Blue Economy CRC first webinar series for the year 2022. I'm Professor C.M. Wang, and I work in the University of Queensland, as well as the leader of the Offshore Engineering and Technology program of the Blue Economy CRC. Firstly, I'd like to begin by acknowledging the traditional owners of the land on which we meet today. I would also like to pay my respects to elders, past and present, and the Aboriginal and Torres Strait Islander people. Now, for those who are not familiar with Blue Economy CRC, the CRC was established with a 10-year life under the Australian government's CRC program. By the way, CRC stands for Cooperative Research Centre. And so right now we have 43 participants from Australia in the Blue Economy CRC, and they are all also around the globe. The purpose of the Blue Economy CRC is to perform world-class, collaborative, industry-focused research and training that underpins the growth of the blue economy through increased offshore, sustainable aquaculture and renewable energy production. Now, after a very successful series of webinars in last year, 2021, we now look forward to providing more interesting topics for discussion throughout this year. Today's discussion topic is floating structures for the next generation of ocean industries. And it's a very, very exciting topic, which has attracted over 475 participants for this particular webinar. Now, we will start with each speaker providing a presentation, followed by a 15 minutes Q&A. So I encourage all of you to use the Q&A function tab below your screen to type in your questions to our presenters. If there are lots of questions, then we cannot cover during the first Q&A session. But our speaker, Hans, the first speaker, will type in some of the answers for you while the second speaker, Vegard, is presenting. Please only use chat if you would like to send specific questions to the panelists. And the panelists include myself, Dr. Naji Abdusami, who is the Deputy Program Leader of the Offshore Engineering and Technology Program, Leslie, who is the Webinar Manager of the Blue Economy CRC, and of course our two eminent speakers. So please use the chat if you like to send specifically to the panelists that you do not wish to discuss in the Q&A, or you're having Zoom technical issues, while our manager, Leslie, will help you out if you have this problem. Now, the webinar will provide two separate presentations from SINTEF Ocean, two research-based innovation centers. In the Norwegian language, I can't pronounce those words. Acronym is SFI, but I'll let Hans and Vegard elaborate on those centers, what it means. So the two centers are SFI BLUES and SFI EXPOSED. And our two eminent speakers for today is Dr. Hans Bjelland from SFI EXPOSED and Dr. Vegard Agnes from SFI BLUES. So we begin this webinar with our first speaker, Dr. Hans Bjelland from SFI EXPOSED. Just a few words about him before he shares his screen. Dr. Hans Bjelland is the Research Director of the Aquaculture Department at SINTEF in Trondheim. The organization has a very broad interaction with Norwegian and international aquaculture industry, conducting fundamental and applied research. Bjelland is also the Director of the Center for Research-Based Innovation on Exposed Aquaculture Operations, hosted by SINTEF with participation from major fish farmers and technology providers. So without further ado, Hans, I will pass this microphone to you and we will enjoy your presentation. Please proceed, Hans.
Thanks a lot, Chen. Can everyone see my screen now? Yes, great. Good afternoon and good morning. It's early hours here in Norway. The sun is yet still not up, but you'll you can see some snow here in an hour's time, I guess. So we are excited to be here and talk about some, to us, exciting research and innovations ongoing. And as Chen introduced us with, we will start with talking about the SFI EXPOSED, which is a research center on exposed aquaculture operations. But first, I would like to kind of give you a frame to see, to try to understand what kind of research ecosystem that these centers are positioned in. So just a few words about Simtef and our role. Our vision is technology for a better society, and to achieve that we have different roles. We do contract research, as you will see, and an important part of our capacity is also the laboratory and software that we utilize, and you will see examples of this in the presentations. We work heavily on developing new technology and knowledge, and also new ventures to achieve that, because we see that to solve the society's big challenges, we need both established companies, but also new companies growing up, taking positions. And we also, as we will be touching upon in today's speaks, we are also taking a part in the dialogue in the society and to look at what kind of knowledge the regulators need to make to make sure that the new industries and the new solutions have the right framework to work with it. The organization, at least in European context, is a large research organization. SINTEF has in total about 2,000 employees. We run about 6,800 projects a year. And SINTEF Ocean, where we work, is a part of SINTEF, and we conduct research and innovation related to the ocean space, which we believe will play an important role in solving modern society's challenges as we see it. And in that, transport, food and energy production represent the backbone of the ocean-based industries. And this is also the backbone of ours. So what we will talk about today is two research centers that very much exemplifies this. We see that the ocean industries are very much intertwined. Aquaculture, which my department works most with, is not a small industry. It's a large industry that encompasses larger and larger vessels. It involves larger structures, very much similar and able to utilize the knowledge gained from also other ocean industries, as me and Vegard will show you today. And we see also that the competence gained through aquaculture technology is also a competence that is valuable both for underwater robotics, seaweed cultivation, etc. So I think I'll give the word over to Vegard to say a bit about these research centers and the research priorities in Norway. Please, Vegard. Should I take the next slide?
Yes, please. Thank you, Hans. As you said, before we go into the details of the centers, we believe it is kind of useful to briefly explain some Norwegian research priorities and the SFI as an instrument. So this is a slide in Norwegian, but I will translate. It's from the Norwegian government's long-term plan on research and higher education, which kind of has three main goals. Firstly, to improve competitiveness and the ability to innovate, and it is to meet large societal challenges, and also to develop scientific communities of outstanding quality. And there are some priorities within this plan, and ocean is as you see down left, one of them. And if you just click one or two times, Hans, one more. Thank you. So SFI is the Norwegian abbreviation for Centre for Research-Based Innovation, and these are important mechanisms for the Norwegian government and the Norwegian Research Council to kind of realize the national plan for research and higher education. And you see that SFIs related to the ocean, they are kind of strongly founded in national strategies. So if you go to the next slide, Hans. Yeah, just to give you also some overview of the overall expectations to SFI, to see what kind of the Norway kind of expects back from these kind of centers. So first, it is that we should develop expertise in fields of importance for innovation and value creation. Further, these are long-term research efforts which should be done in collaboration between industry and research institutes and universities. So a similar type of setup as CRC centers in Australia. Further, we are expected to enhance technology transfer, internationalization, such as this, and researcher training. And of course, the scientific merit of the center that must be of high international standard. So that's kind of the basis for what we are trying to achieve with the centers of research-based innovation. So that was just to put the centers in a kind of Norwegian strategic research context. So I think now Hans will continue with his presentation on the first of the centers, SFI EXPOSED.
Yes, thank you, Vegard. So I'll talk about exposed aquaculture operations, both what we do in the center, but also give you a presentation of the current state in Norwegian aquaculture and globally. And this center has been ongoing since 2015, and we are now in the kind of the later stages of the center, and we will end the center in a year's time, probably. Which is part of the kind of the duration of such a center. So to give you a sense of conventional salmon farming, and I have to say that although other species are highly relevant and we are very interested in and eager to explore the possibilities of those, it must be said that salmon is the main driver in innovation in Norway, and also very many other places as Australia. Conventional salmon farming is already a large-scale industry, and just to give you some numbers and some idea, we see pens of 160 to 200 meters in circumference, with each pen holding 1,000 metric tons of salmon in each pen, and that equals 2,200 cows in each of those pens. And as you see from the picture here, you have several pens in one, and this is a large but not an uncommon site. And as you know, also from Tasmania and elsewhere, feeding is very much done by dry feed pellets, although we see explorations of other ways of transferring pellets to the fish. And monitoring and feeding is very much done from land, as you are also seen in Australia. And vessels become larger and larger. We have these smaller workboats at the sites, but then specialized vessels for anchor handling, special operations, as well as wellboats that can have a capacity of around 4,500 cubic meters. Yeah, so they're already large and it's already fairly exposed, but there is an ambition to explore that even further. And as some of you might have seen, there are some large-scale, ambitious efforts in Norway at the moment, and very much of that is driven by an governmental incentive called development licenses that was introduced in 2015. And by the end of that window, there were 104 applications handled. I don't have the exact number of granted applications, but it's lower than that, so obviously, but there are already a couple of large-scale structures that has been employed. So this is kind of but we see that there is a movement from the traditional cages that we see a large potential for still. There are robust, cost-efficient. We have a lot of experience. A lot of the auxiliary systems are based on that. But then there is an incentive to explore both closed containment systems, both on land and in sea, and also these larger, stiffer, more rigid structures, maybe submersible structures going more offshore. And we also see that also globally, it's important to have the right distinctions between sheltered, exposed, offshore, open ocean. There are lots of expressions floating around. Exposed and open ocean, offshore is not the same for everyone, and there are efforts to kind of find a united way of operating these distinctions. So in another way of illustrating this, we see that there is a potential also from going more exposed with the current technologies, but there are some limitations there, obviously. There are a great interest in going more, as I said, to closed containment systems on land and at sea, and then going further offshore by utilizing new structures. And the Research Centre Exposed handles both the current technology, but also the opportunities given by these new structures. A research center as this, a Center for Research-Based Innovation, is, as Vegard told, a long time collaboration between industry and academic partners. SINTEF Ocean is the host of this Exposed. And then we have 3 of the major fish farmers participating. That's Movi, Cermaq, and SalMar. And together with Norwegian University of Science and Technology, Institute of Marine Research, and then some important technology engineering and certification providers such as Kongsberg, DNV, MacGregor, and Scale AQ. The outset of the research center that we are heading is that although all of these partners handle and work with exposed aquaculture daily, there is a need for for collaboration to find the solutions for these some large and important challenges of this. And we also, in our name, we focus on the operations, and that's our focus. We can design structures that is very fitted to be in those environments that we are looking at. But the most important question is making structures, vessels, all that we need to put there, operate or support the operations that will be handled there. So that's why we divide in some research areas focusing on the technological innovations like autonomous systems, because we believe that farms at exposed sites need to be more autonomous. We need to be less dependent on manual labor. We need to have a better understanding of the system so that we can prevent things in advance. And that's why we also need monitoring and operational decision support and strengthen that. We need to work on the structures which Vegard also will talk more about in his presentation, and vessels. But we also need that these systems interact with each other. We need the relative motions between structures and vessels to be handled. We need dynamic positioning of vessels in a way that makes it possible to operate and conduct operations, etc. And then on the other hand, we see a need to put this into an umbrella of safety and risk management, as well as make sure that the fish behavior and welfare is handled. Because different from oil and gas and offshore wind, aquaculture is really dependent on providing a good habitat for the fish, and that's all the reasons why we are there. And so we have to understand those limitations, and and also to give you a kind of an impression of just a normal day at the site, and fish farmers will very much recognize this. This is just a normal day, and this is not offshore at all. This is sheltered conditions. But I like these videos because they illustrate that already here there are some limitations to conducting basic operations. We know that aquaculture is one of the most risk-induced labors of Norwegian society already. We know that there is difficulties in conducting daily operations. We also know that vessel operations become more demanding in these conditions. We might be concerned about fish welfare, but not in these conditions at all. We have done extensive research on the swimming capacity of salmon. What we are still ongoing in our research is to understand how the fish behaves and copes with higher waves, and how the structures can afford for that. And we know also, which is a huge challenge in Norwegian aquaculture and a huge concern, is that there is a increased risk of escaped fish in bad weather. So first, what we have to do is understanding these conditions physically, and we see that although the structure is, of course, and in designing the structure, it's of course important to focus on the extreme values. We see that to conduct operations, there might be other parts of the environment and the statistics of that might be important. We have been doing verification studies of most of the new designs of aquaculture designs both in Norway and also some international concepts, which gives us a lot of knowledge and insight into what kind of challenges that we see also. These are typically some of the last things that is done to verify that the designs are correct, but we also utilize these methods to explore the physics, because these are very complex. This is very complex physics that we need to understand. And for example, the interaction between flexible nets and rigid structures makes them different from other ocean structures. Vegard will probably get into some of that later. And we also see that digitalization and automation will be important. This is important for all aquaculture, but will be even more important for when we move offshore. We do a lot of work on automatic systems and ROVs because the industry is already moving away from using divers, and the focus has been more on ROVs. And then the opportunities for automation, for example, hole detection, inspection routines is increased. So we make autopilots, navigation systems, etc. We use and we see that the industry is developing systems for machine learning, using face recognition, looking at schooling behavior, for example, which becomes an important tool in moving from looking at this as 200,000 fish in a pen towards individual fish and treating fish individually. We see that digital twins will be an important part for operational planning and also vessel designs. And we utilize other modeling tools to inform both site selection and site design. So, starting to wrap up, we see that there are different needs and capabilities also in such a center, and we see that the fish farmers, what they need is to share experience. There's a huge benefit in doing that. They need improved procedures, utilizing knowledge that's practicable, and they need a center as this to develop best practices, for example. They need to have some limits to what kind of sites they should stock which type of fish in. And of course, they need novel products and services provided by others. And the technology and knowledge providers, they need shoulders to stand on. They need to make sure that they are on the edge of what has been developed. In a center as this, they need access to end users to really understand their issues. And they also need a kind of a sandbox to test ideas and solutions. And sometimes some of these innovations that they are working on will be handled within a center, and some in more associated projects. And then, of course, an important part of this such a center is also educating students, which the companies will need. So we, for example, have about 15 PhD students that will be finished within the center's duration, and a number of master students that we see. There are examples of that go straight into some of the companies that are participating in this. And finally, we see that society, they need visions and roadmaps for the future of an industry, and that's really a global issue. we see a tremendous interest in how we can utilize the oceans for aquaculture. And this is my last slide. Then we see that external conditions will be key. We see there are a number of examples that regulations and incentives, they drive innovation. And both in Norway and elsewhere, we see that fish farmers are dependent on a license to operate. And this is also true for exposed and offshore aquaculture. So we have to make sure that when doing new ventures into new ocean areas, this has to be done right. And I think that all can agree to that. There is global interest in developing a beneficial regulatory framework. I mentioned the need for having a unified way of looking at exposure levels. There is an ICES working group looking into this as well. Yeah, and we also acknowledge that there are some important regional differences between the concerns. There are, yeah, such as marine spatial planning, sector overlap, wild salmon, as is important in Canada and Norway. Whale entanglements is an issue in US, I know. Visual pollution, indigenous people, benthic impacts, and fish welfare, of course. The Norwegian government set up a working group on looking at how we best can unify the different regulatory bodies and regulations for the Norwegian aquaculture, because we see that although quite forward-leaning already, we see that it's becoming fragmented, and there's a wish to develop a more unified and future-proof way of handling the industry, and I'm part of that working group, which will hand over its report in a year's time, recommending how to do this in Norwegian context, and that might be of interest also for globally. So with that, I end my talk. I'm happy to answer questions either now or in the chat, or and Chen, you have to.
Yep. Yes.
I don't
Thanks,
know how much. If we have time for questions straight ahead. Yeah.
Thanks, Hans, for a very fabulous and informative presentation on floating structures for aquaculture, challenges, and also the research directions and the issues to address. Very, very innovative solutions to farming fish. I think the Norwegians has made this topic of aquaculture a very sexy topic to pursue. Everybody is getting it because it's so exciting. Now, we have a few questions. Before I look at some of these questions, I note that you showed a video showing a very rough sea state condition, and you say that in Norway that's sheltered. So I was a little bit puzzled, because if you bring it to Australia, for example, we will be exposed, and I think if you look at Singapore context, it'll be ocean kind of time space. Can you comment on the parameters in which you can separate between, say, sheltered to exposed to the offshore to ocean? So what is your take on this, on how you categorize them?
The easiest and most conventional way of separating is kind of in terms of wave heights and
okay.
And so when talking about sites in Norway, farmers tend to talk about the extreme values of especially in wave heights, and then we talk about
okay.
But in these conditions, that might not be the most relevant. We see that there are some sites that might have once a year a wave height of I don't know, 4 meters.
Right.
But that's not really what's hindering them in their daily operations. We have sites that have been abandoned due to bad weather, and for longer periods of time.
Yep.
Which is a larger problem.
Yep.
Actually.
Yep, that's right. So it's not just distance; it's also wave height and so
yes.
on. Yeah. Okay. There's a question from Anthony Hammett. He asked, you probably know that in the year 2018 there was a mass escape of 20,000 farm kingfish at Port Stephens in New South Wales. How often do you have accidents that result in salmon released in Norway?
Yeah, there escape incidents. They occur after some new regulations in, I might be mistaken, in around 10 years ago. The escape incidents, the number and the scale has dropped tremendously. I don't have the recent numbers, but I think that we see statistically around 150,000 salmon escaped in total, which is a small number compared to the number of fish standing in the ocean at all times. But it's a high number compared to the number of wild stock salmon, which is about 400,000 salmon. So it's a concern.
Yeah. Yes.
And it might be improving, but slowly and yeah.
Yep.
So, and we can't really, if we want to expand in the industry, we want to take it into more rougher conditions. We can't really accept that will mean that we will increase the number of escapees. We have a zero vision.
Yep. And another question is from Roger Espejo. He asked, what are the regulatory challenges that exposed aquaculture developers are facing right now in Norway? The regulatory challenges. Actually,
what the largest challenges are, I would say, is the lack of regulatory systems once you go offshore, because then you don't have the same maritime spatial plannings. You don't have the same. We haven't really gone up that path yet to make sure that the right concerns are covered. So SalMar, which is now applying for a site that is really offshore, is kind of everything needs to kind of adapt to that. And that's one of the reasons for the working group that I'm sitting in, to get ahead of that development.
Yeah. Oh, okay. I now pass to my fellow panelist, Dr. Naji Abdusami, to ask some of the questions that have been posted on the Q&A tab. Naji?
Yeah, thank you very much, Professor CM, and thank you very much, Dr. Hans, for this interesting presentation. I think there have been very interesting questions overall. If I summarize them, I mean, one of two for the time being, and then maybe Dr. Hans can answer them in the chat. Basically, around the design codes and the standards available for designers, in particular those large offshore structures for aquaculture industry, and the kind of HDPE BIBIS and elastic structures. Do we have any available design codes and standards?
Yes, we do. DNV has been one of the important actors in this space, been involved with many of the new designs. And when as SalMar is now one of the large fish farmers that really has explored these opportunities, now kind of challenge the regulatory bodies in their efforts. They have also been challenging the technical standards because the current ones that we had for more conventional systems were not they're useful but not enough. So I know that the DNV is one of the actors that has developed their new system for evaluating such system structures.
Yeah, thank you. Thank you very much. There's another question, I think, related to the design of the closed containment that I think you showed in your slides. And in particular, if there is any mitigation strategies for the tank sloshing, especially in rough sea condition and then including the motions or the rigid body motions, then sloshing become maybe a little bit problematic. So can you comment if you have any type of...
Yeah, I would have loved to talk more about that. Time didn't allow it, but sloshing is a concern, and obviously we are probably not looking at having these systems at really rough seas. But what we have seen is that with sloshing, as some of you might know, it's not just the amplitude of the waves, but also the frequency that is extremely important. And we see that some of the eigenfrequencies of these systems unluckily hits the frequencies of the waves in Norwegian shores. So we have to kind of design around that. And we have done extensive studies in our laboratories to study this phenomena, but which is sloshing is not new. This is known for other systems as well, but sloshing in aquaculture systems is still something somewhat new. You had a fish that will fish, and also the internal currents that will affect how the sloshing will behave. So we're working on designing around that. Yeah.
Thank you, Dr. Hans. I think that's all in terms of the engineering. I think challenge it, Professor CM, back to you.
Yes, thank you. You know, time passes very fast because when we are talking about something exciting, it takes your time senses away. So you kind of lost time. Okay, so without further ado, I'd like to introduce our second speaker, Dr. Vegard Agnes from SFI BLUES. Vegard works as a research manager for the marine structures in SINTEF Ocean and is the center director for SFI BLUES, floating structures for the next generation of ocean industries, a center for research-based innovation. He obtained his PhD in marine civil engineering and a Masters of Science in Mathematics, both from NTNU in Trondheim, Norway. His research has focused on dynamic response of floating structures for offshore oil and gas, aquaculture, floating bridges, and offshore wind. So, Vegard, I hand the time over to you. Please proceed with your presentation.
Thank you, CM. Can you see my screen now?
No, not yet.
No.
You got this.
What button?
Yeah, got it.
No?
Got it.
No.
Got it.
Okay, good. Yeah. Thanks again for the invitation and for the opportunity to present our research center, SFI BLUES. So in this part of the webinar, I will present what SFI BLUES is, why we have the center, and also give a taste of some of the ongoing research. The center, we have a vision that we will develop, that we will have floating solutions to present and future industrial and societal challenges. And the main objective of the center is to develop tools, methods, and knowledge to enable new floating structures for renewable energy, for aquaculture, and for coastal infrastructure. And as I said, I will, in the presentation, try to explain why we have this vision and what we are doing and planning to do in order to achieve this objective of ours. So first, some kind of basic facts about the center. You now know what the Center for Research-Based Innovation is. So this is one. We are a new center. We started last year, and we have funding for 8 years. So we are still early in the center. So budget-wise, I'm not sure what currency which is most relevant here, but I put in also Australian dollars. So it's about 30 million Australian dollars over the period. Of this, half of this comes from the Research Council of Norway, and the rest of the funding is cash and in-kind contribution by the partners in the center. SINTEF Ocean is the host of the center, and we have a consortium with in total 15 partners. 10 of these are what we call user partners, which are industry and public partners. 2 of our partners, they are what we define as end users. Equinor, may be familiar to some of you, a large Norwegian oil energy company, which has transitioned from oil and gas and is now working more and more actively with, especially with offshore wind, but also have interest in floating solar. Then it's the Norwegian Public Roads Administration, which I will come back to this. It may seem a bit odd to have the Public Roads Administration in a center like this, but Norway has a rough coastline, and the Norwegian Public Roads Administration, they are doing a lot of development work on floating bridges and submerged tunnels, submerged floating tunnels. The other 8 user partners, they are technology providers and engineering companies mainly. Some of these are international companies and some of them are more Norwegian. I don't think I will go through all of them, but you see the logos here to the right. The research partners we have 2 SINTEF institutes. So in addition to SINTEF Ocean, we also have SINTEF Industry, which is specialists on material technologies. Then we have the Norwegian Geotechnical Institute. We have the Norwegian University of Science and Technology, NTNU, and we have the Norwegian Meteorological Institute. Yes. Okay. So a bit about or quite a bit about motivation for having a center like this. Of course, we know that there are some grand global challenges, and the UN Sustainable Development Goals. That's our common commitment to solving the challenges. So that forms the basis also for this. Actually, that forms the basis for everything SINTEF does, but also this center. So we know that there's an ongoing transition in the world's energy mix to meet the goals of the Paris Agreement. So there's a kind of global need for clean and renewable energy. Also, there are changes in diets and an increase in the world's population that generate increased need for safe and healthy food. And there are requests for increased mobility, and there's many places a shortage of land area. So that introduces need for resilient infrastructure in coastal waters that can be used for transportation, but also for industrial and residential developments. So as and the ocean can obviously contribute with solutions here. That is kind of highlighted on top-level politics, such as illustrated here with this high-level panel for a sustainable ocean economy, where both Australia and Norway are members and active. So what does floating structures have to do with this? Obviously, they are relevant for highly relevant for many of these applications, and they can kind of be designed for almost any area of use. They're kind of flexible by nature and can be adapted to different water depths. And also they can be kind of designed to minimize environmental impact and also be geared towards kind of decommissioning, recycling and reuse in a much more efficient way than bottom fixed structures. And they will clearly be part of ocean-based solutions to global challenges. So here's just a slide showing you what kind of structures we are talking about. Just these are illustrations of concepts that user partners in SFI BLUES are working on. These are just to kind of, we're not limited to these, but these are just to give us a taste of of the type of structures. So up left, you see a floating wind farm. Up right, you see a floating solar structure. Down to the right, there's a concept for, it's not actually a concept, it's a real structure for exposed or offshore fish farming. And to the left, you see a very large floating bridge, which is planned in Norway. So we will now go a bit into the kind of technical potential for each of them to understand why it is important to focus on the structures and a bit of their role in development of future ocean industries. So if we start with floating offshore wind, obviously I guess we all know that the potential of offshore wind is large, and it can cover the world's energy consumption multiple times. So I'll show this from a European and a Norwegian perspective. So in Europe, there are ambitions of developing about 450 gigawatts within 2050, and there are estimates that 100 to 150 gigawatts of this will be floating. I'm a hydrodynamics and structure guy, so for me it's easier to talk about units, floating units instead of gigawatts. So I like to transfer this to units. So if we take 15 megawatt turbines, which is a very large turbine, not yet to be built, but this is kind of the sizes that we are working on in research at the moment, then this is equivalent to 10,000 floating wind turbines in European waters by 2050, which is it's a very, very large number. So the potential here is massive, but still it's a costly source of energy. And then just briefly also about the status of offshore wind in Norway. Norway has been quite early with floating offshore wind, with the demo turbine from 15 years ago, called a high wind demo. And now, I think next year, the first larger wind farm called Hywind Tampen will be in operation with 11 8 megawatt turbines. And this is a wind farm to electrify two oil and gas platforms. So Wind Europe, they have some estimates for what could be built in Norway. They say like 30, say that maybe 30 gigawatts could be a good number for Norway in 2050, but there are not any clear kind of number on this from the Norwegian government yet. There are two areas that will be opened on the Norwegian continental shelf, and that's one location called Sørlige Nordsjøen 2 with 60-meter water depth, where bottom fixed is most likely to be built, and they will have they will open for 3 gigawatts. And then they will open an area at Utsira Nord at 200-meter water depth, where floating obviously will be the solution, with 1.5 gigawatts. However, at the moment, just these days, there's a large political discussion in Norway due to high cost of electricity. So it's a national debate at the moment, also regarding offshore wind. Should we allow export of electricity or not? So this, unfortunately, at least at the moment, it kind of slows development down a bit. But at the same time, the government has said that they will they will start the process and identify more areas for offshore wind. So hopefully, the more areas will be available soon. Yeah, because these numbers are still quite small compared to plants in, for instance, France and Scotland. Yes, if we go to the next application here, we go to floating solar. This has it's a booming market where the interest has increased exponentially over the last 5, 6, 7 years. But still, most installations are in lakes, dams, and reservoirs, so inland water bodies. There are some prototypes in more exposed areas. So just here also, it's nice to look at the potential. The first one is an estimate from Singapore, from CERES, saying that if you cover 1% of the total surface area of man-made reservoirs, this can give 400 gigawatt peak of floating solar, and this corresponds to 600,000 of this floater that I showed earlier. So that's also just to give a taste about the numbers and sizes here. Of course, potential in the ocean that comes in addition, and that's of course huge. There are some estimates that if you cover 0.2% of the ocean surface with solar, that can cover the total global energy need in 2050. But 2% of the ocean surface is still a very large area. It's not small. Just some slides about the floating solar in Norway. This is just an example of a floating solar structure where there's a membrane connected to a floating collar from an old fish farm. So this is actually producing electricity in relation to the fish farming site. Yeah, and the same type of concept is now being installed will be installed at the Canary Islands. So it's a Norwegian concept that will be installed in Pukan, Canary Islands. Another concept that is being that there are plans for testing near offshore, near quite exposed aquaculture sites in central Norway is this more modular type of system that is developed by AMOS Maritime and Equinor. So there are, even if Norway is a high latitude country, we are also working on technologies for solar. Hans covered aquaculture very well, so I will not go much into details here. I will just kind of remind ourselves about the two main directions that we see in Norway, at least with respect to structures. It's closed containment systems for more sheltered areas, and then new concepts more offshore-like for exposed and offshore areas. I think I will just leave it there with aquaculture. To understand the coastal infrastructure in this Norwegian setting, we need to start with something called the Coastal Highway Project, which is to the right here. You see a map of Norway, and the orange line here is the Norwegian Coastal Highway, and there are several deep and wide fjords that needs to be crossed. Most of these are now crossed by ferries, but due to water depth, it's not possible. So we'd like to get rid of the ferries and have them open 24/7. So an obvious choice would be underwater tunnels, but some of these are too deep for traditional tunnels. So floating bridges and floating submerged tunnels are kind of attractive solutions to make this road ferry free. So over the last 10 years or so, the Norwegian Public Roads Administration has been working heavily with the developing technologies for fjord crossings. And what you see this figure up right, this is kind of one of the most maybe the bridge which is closest to realization. This is almost 5 kilometers long. But of course, there are other coastal infrastructure which can be important as well. floating structures can be an attractive alternative to land resources. Of course, there are examples that CM knows very well, for instance, with multi-purpose facilities in Singapore, floating airports in Japan, and floating cities. But there are also more and more use of floating structures in kind of simpler, with kind of simpler applications so there are, for instance, floating swimming and swimming area in Oslo, some floating houses for tourists, and some islands for recreation in Copenhagen, just to show a couple of examples. Yes. Yeah, and obviously, most people in the world, they live close in large cities close to the ocean. So utilizing the ocean also close to the cities, that's interesting. Okay, so now we have shown several examples of applications that are important both for Norway and beyond. And now we need to kind of look into what they have in common. Of course, they are floating, that's obvious, and they can contribute to some mentioned challenges. But in order to harvest solutions, there are several research questions that needs to be answered. And many of these research questions, they are kind of common to a wide range of applications and markets. And this is where SFI BLUES comes in. In SFI BLUES, we will address common research needs and thereby try to accelerate innovation. And first, in the applications that we have shown now, but later we also hope that the knowledge and methods and competence that we develop in SFI BLUES can open up for completely new types of floating structures for other purposes, like for geothermal energy, for hydrogen production, storage, for energy islands, recreation, and so on. Yeah, and so let us look a bit into how we can organize the work inside the center, how we work to achieve the goals. So we have defined a total of 7 work packages or research areas that you can see here. I will in a minute show you some details on each of them. But here you can see that we are kind of working on 3 layers, one with new concepts, one with tools, and then one with basic physics. And we try to make all of these research areas to interact, to improve design and enable new concepts. So let's briefly go through the research areas. The first one is novel concepts, which is not really a research area as such, but it's a place where we try to meet industry and research partners to identify and understand knowledge and technology needs and try to convert this into research activities that can be addressed by the other research areas. Yeah, so this is like a meeting place, and at the moment we address the research activities through use cases, and the ones that we are focusing on now are floating offshore wind, floating solar, floating bridges, and aquaculture. So we'll come back to some more details about those. The next one is something we have called Digital Fjord Lab, but what it basically is it's a research area where we're going to develop a digital framework for researchers, or a development framework for researchers, which will enable researchers like me, which is working on hydrodynamics and structures, to make use of high-end IT services such as cloud computation, storage, web interfaces, web services, and so on. And we believe this is important because this helps digitalizing the knowledge that we develop into into software. And the reason why we want to develop the knowledge into software is that it makes the results more accessible to user partners. Many research projects, they end with technical reports, papers, which is good. We also need to do that. But for an industry company to pick up a technical paper and to implement that in their daily work, that may be a hard task. So this is a way where we try to reduce the threshold for utilization of the research. Yeah, and then next research area is about design optimization. This may be familiar to some of you, but this is really about trying to understand what is a good design, or what is the best design. And this is not an easy question or easy task. First of all, you need to define what you mean by best. Up right there is just an illustration from an airplane, where the kind of the answer to what is best depends very much on your subject. Or so what is the best airplane in terms of manufacturing may look very different to what is the best airplane in terms of flight control, for instance. This is where kind of one particular technique comes into play, called multidisciplinary design optimization, that we have worked on for some time with applications to floating offshore wind, and we start also working with these techniques on floating offshore wind in the center here, but hopefully we can use these techniques for all the types of structures later in the center. Yes, we have another research area related to the marine environment, and here kind of the overall goal is to improve, broadly speaking, metocean models on a range of scales. So we are basically working on metocean models from offshore and into the coastal areas. So some of the things that we are doing at the moment is that we are improving ocean reanalysis methods. So that's for offshore, by including ocean parameters such as mainly current, to achieve a consistent hindcast data sets with not only wind and waves that we normally have, but also to have consistent current models in there. We also work on wave modeling when we approach a more complex terrain like we have in the Norwegian coast, and there we have to kind of increase the spatial resolution of the wave modeling. So there, we have started now work to improve wave modeling down to a resolution of 100 meters for hindcast data in Norwegian fjords, which kind of will improve metocean design basis really for coastal structures. We also have some work on inhomogeneous waves, so in fjords and their effect on large floating structures. And not at least, we are also working on within this research area, we are working on improved waves in laboratories, which is obviously an important thing for SINTEF Ocean, as we run one of the largest ocean basins in the world and are now starting to build a new one. So that's important. We go to wave structure interaction. There, the first focus area is to look into structures that cover large sea surfaces, and we have kind of identified two types of structures that we start looking into. First, it's structures with membranes and elastic tubes. So here, just illustrate with a floating solar concept upright, and below it's a membrane-based cage for fish farming. And the second type of structure that we are considering is multi-body or array multi-body structures or arrays of bodies. Two examples below here. Below left is a floating solar modular structure, and to the right, it's part of a floating bridge, which is also like a modular structure with an array of pontoons. So the goal here is really to develop rational models through a combination of analytical, numerical, and experimental work. We have a research area on materials, and this is not the goal of this is not to develop new materials, but it's more to bring some additional materials into the toolbox of the designer, in addition to steel and concrete that is normally used for offshore, at least. So aluminium is important because we have a large aluminium producer as one of the partners. Thermoplastics is of course used in aquaculture, but can have other usages as well. And membranes is a topic that we see can be used for several purposes. I think I leave it with that and go to the next. This is the last research area, and that's mooring and anchors, which is kind of obvious components for floating structures to be held in position. And there the goal is really to develop solutions that really keep the structures in a location in a safe and sustainable, cost-efficient manner. So the first study that we are working on here is really to kind of bring global analysis competence together with geotechnics to develop more integrated tools where we combine mooring lines, soil, and anchors in a more integrated manner than what is normally being done. So this makes us able to study like mooring line induced trenching, for instance, at the seabed, and also more effectively how the mooring lines are interacting with the anchor and so on. Yes. So this was kind of a short introduction to 7 research areas where there are lots of things that we could have discussed, but it's difficult to go into details in a webinar like this. But hopefully this gave you an overview. So we have kind of talked about what SFI BLUES is. We have talked quite a bit about the motivation behind the center, and given you an overview of some of the research activities that's ongoing. And of course, we're always interested in possible collaboration, so feel free to get in touch. I'm not alone in this center, as you see, so here's a picture of the whole center from this autumn. Yeah. Okay. Thanks.
Thanks, Vegard, for a very excellent presentation of what SFI BLUES are working on, as well as the various interesting applications of very large floating structures, from renewable energy production to aquaculture to infrastructure and so on. So I think here we will look at some of the questions that has been posted on the website. But before I do that, I received an email message from Anders Arfelt from California Seasteading Institute. And he has one question to ask you, which is relating to regulatory regimes of novel floating structures. You know, novel floating structures may challenge a broad spectrum of existing maritime regulations governing the operation of ships on the high seas and in national waters, mainly those of the IMO and the ILO, as well as the classification societies, to name a few. So this question is, has the scope of regulations that will need to be adjusted to enable and permit novel floating structures that are aimed at new and even innovative business models being identified?
The short answer is that it's not part of the research areas in this center, but it's a really interesting topic, I think, and one thing is the global rules and regulations, but also from country to country there are interesting aspects. See, Norway, even if we have a large area at sea, there are several users that would like to use the area for various purposes. Floating offshore wind will need a lot of area. Offshore aquaculture will need a lot of area, and there will, of course, there is ship traffic and so on. And I think one really needs to cooperate in order to have a good exploitation, which enables everyone to do their business there.
Yeah. Another question is this, you know, so far a lot of applications are single-purpose floating structures application. So when you have some kind of a co-location of or integration of, say, two different types of applications, namely, for example, if you're combining renewable energy production plant with aquaculture to supply the power, is this one of the research areas that SFI BLUES are looking at, the multi-purpose function of floating structures?
Not directly, not at the moment, but again, that's very relevant, and definitely I think it's possible. But based on discussions with industry, I think this one of the main challenges is kind of business models around this, because normally a company is either an energy company or it's a fish farmer. So the energy company would think of fish farming as noise and vice versa. They're mainly interested in their own application. But for sure, like offshore fish farming, they would need clean energy. So renewable energy production nearby, offshore aquaculture, for instance, that's I think that's more likely than having them in the same structure, at least.
I see. Yep.
Yeah.
Thank you for answering the question. I'll pass this Q&A session to Naji to read up some of the questions for you, for both, maybe for Hans as well as for Bhagat. So Naji, would you like to take over and have a look at some of the questions that we post on the Q&A?
Thank you very much, Professor CM and Dr. Vegard, for this excellent presentation. I think probably that question, I mean, overall, that any new development or a novel structure is going to, especially if we talk about new development at sea, there will be a concern about the environmental impacts, in fact. So how those environmental impacts are incorporated, for example, when it comes for floating offshore wind versus floating solar design, for example? I mean, have they been considered or left out at this stage?
Yeah, it depends what if you're thinking about SFI BLUES, it's not directly a research area as such, but of course this is something that Hans was talking about, license to operate for fish farming, but I think environmental impact of both floating offshore wind and floating solar, that is also kind of the foundation for a license to operate for these applications as well. So we have a parallel center to this as well, which is solely focusing on offshore wind here in Trondheim, called Northwind. And there, this is one of the key research areas, environmental impact of offshore wind. So it's definitely something we are working on within the SINTEF and our research partners. Yes.
Thank you very much. The other question, I think, we know that Norway, I mean, is leading in lots of research in terms of the offshore development for both aquaculture industry and energy industry. But when we compare, I mean, with other places like Australia and maybe New Zealand in terms of the extreme weather conditions and so on. So I wonder, what are the design criteria, or in fact, the return period that you apply, for example, design floating offshore wind versus solar versus aquaculture structure? Are you adopting some cases or some similarities from oil and gas industry, or there is a new requirement from your experience?
There are new standards being developed. Many of them are relying on, or at least referring to, offshore oil and gas. But of course, the consequences of failure are different with a floating offshore wind farm compared to offshore oil and gas. With offshore oil and gas, you have large environmental impact if you have catastrophic failure, but within offshore wind, it's mainly economic loss. So I think safety factors will, in general, go down. You talked about return periods. I think standard ultimate limit state design in oil and gas in Norway is 100-year return period, and for floating or for offshore wind, I think it is lowered to 50. Yeah, and for aquaculture, I think also it's 50. But Hans may correct me if I'm wrong. Yeah. For floating solar, I'm not aware of detailed standards like this. I know DNV has developed a standard for floating solar, but it's quite fresh, and it's a new area. So I think there will be development on the standard side with respect to floating solar in the coming years. Yeah.
Thank you very much for your answer. I believe there are also many interests that I can see here about the floating solar, or I mean marine solar in general farms, and then how they compare with the land applications. I mean, if you have a BV land application versus the marine application in terms of efficiency and energy.
Yeah, that's definitely out of my competence, but so I have to refer to others. But what I hear is that you can have increased efficiency when you put them on water, because at least if it's very close to the sea, because the water will have a cooling effect, which is positive for it. Improves efficiency of solar panels. Yeah.
Yeah.
Thank you. I think the last question, which is also around the circular economy, and then making recycling of those materials being used in the construction. So what's your aim? I mean, when it comes to emissions, for example, we set a date, or the nation set a date like 2050 to be a zero or so. So what about when it comes to the circular blue economy or circular economy in general? Do you set, for example, certain goals to use some green materials for the current development or future development, or what's your vision, or I mean, what's your view on this?
Yeah, that's a difficult answer. Short answer, difficult question. Short answer is that no, we don't have any kind of clear ambition like that. But I think that there will be more and more requirements also on the material side, that these needs to be zero emission, like throughout their lifetime. So kind of, yeah. So I think recycling, reuse, things like this will be more and more important, and also on the manufacturing side, that the emissions are as low as possible. That's for sure. Yeah.
Thank you very much. That's all I think, Professor Sim, from my side.
Thanks a lot.
Yeah,
Vegard, I just want to ask one question, because there's interest in building floating solar farms off the coast of Brisbane, and Brisbane is sometimes hit by cyclones. Is there a possibility of having solar panels that will be able to be submerged underwater to be protected from the strong waves, or is there's no solution for that kind of thing except towing the whole entire farm away when you hear this storm coming? Is there any development in the area of how to cope with very strong waves and strong winds and during storms for floating solar farms?
Not that I'm aware of, no. But maybe. So now you're talking about rare but severe weather. So that's
severe weather,
yeah. But to some, which happens seldom. Yeah.
I see.
Yeah, no, no, I'm not sure. I haven't seen the development like that. But and I think like floating solar for offshore, that's still very early. It's it's to be developed. I think. Yeah.
Okay, I think we are almost our time is almost finished. I want to first of all thank our two evidence speakers for taking time off and really prepare the slides and give us such a nice presentation. I know it's difficult for them. It's 6 a.m. in the morning to 7 a.m. So it's been tough, especially in Norway, getting up in the cold weather. So thank you so much. Also, I would like to thank all the participants who attended this seminar. I hope it has been useful for you and for your career. Now note that this webinar is recorded and the recording will be made available on the Blue Economy CRC website in the coming days. So if you want to, revisit this webinar again, you can do so. Also, I'd like to encourage you to check out the Blue Economy CRC events page for upcoming webinars. We try to do it once a month. So with that, I like to wish all of you a very good day, and we'll see you again in the subsequent webinars of the Blue Economy CRC. Thank you so much, everyone.
Thank you.
Thanks for having us.
Yeah.